All right, so this video, of course, we will do some example problems for conservation of energy with rotational motion. We found last time that basically everywhere we have kinetic energy, we replace it with two forms, 1/2 mv squared and 1/2 I omega squared. Okay, so now when an object can move, it can both move linearly and it can rotate or spin. So kinetic energy has two pieces, a linear piece and a rotational piece. Of course, we still have the same types of potential energy, mgh and 1/2 kx squared, depending on what's in the problem. And we found that anywhere we have an I, generally speaking, when we use conservation of energy as an equation, if, for instance, we want to calculate the linear velocity of the object at the end, or something like that, what we're going to do probably is replace I, the moment of inertia, with some number times mr squared, where the number depends on the shape. If it's a solid sphere, or it's a ring, or a cylinder, or a hollow sphere, or whatever, each one of those shapes gives rise to a new number, 2/5, 2/3, 1/2, 1. And so everywhere we see an I, we're going to replace it with that 1/2 mr squared or whatever. And also, we have the fact that omega is related to V over R. And this is helpful if, let's say, I want to know how fast the ball is rolling at the bottom of the hill. Well, I want to know the linear velocity. But my conservation of the energy equation has an omega in it. And I don't know anything about omega. I want V. All I have to do is everywhere I see an omega, I just use V over R instead. And with all of this, we can now do some actual calculations. We can take real problems and try to solve them. So let's do an example. Here's an example. Let's say we have a hill. And I have a hollow sphere. And I want to know how high will the sphere rise if you give the sphere an initial velocity of 20 meters per second. All right. So, conservation of energy says kinetic initial plus potential initial is kinetic final plus potential final. Kinetic initial, 1/2 mv squared plus 1/2 I omega squared. And then potential, mgh, and there's no spring. Final position, 1/2 mv squared, 1/2 I omega squared, mgh, and again, no spring in the final location as well. All right, so now let's start asking questions. For our system, the initial state, you've set this ball into motion, this hollow sphere. You've given it an initial velocity of 20. Is it moving yet? Yeah, it's moving. So we have to keep 1/2 mv squared. And then, of course, we know if the thing's moving and it's allowed to roll, then it's also rolling. It's already spinning. 1/2 I omega squared. All right, the initial position. Am I some distance above the ground yet? No, I'm at the bottom of the hill, so no mgh. Final position. I've rolled up the hill as high as it can go. At this point, am I moving? No. If I'm as high as I can go, I must have stopped moving. Because if I'm still moving, then I'm still going up. I'm not at the top yet. So 1/2 mv squared must be 0 because I had to stop. And if I stopped, I can't be rolling anymore. So there's no 1/2 I omega squared either, because I can only be spinning if I'm moving, if this is a rolling situation. What about mgh? Am I some distance above the ground? Of course, that's the whole point of the problem. So mgh is there, and I'm looking for h. Can I solve for h? No, there's too many unknowns. I don't know what m is, I don't know what I is, I don't know what omega is. So I have to use my little trick. The trick says, everywhere you see an I, replace it with whatever the equation says to replace it with. So here I have an I. What type of shape is this? It was a hollow sphere. Hollow sphere, if I look back at my table of values, it was 2/3 mr squared. And the other trick was replace omega with v over r. So instead of omega squared, it's v squared over r squared. Don't forget the squareds. It's really easy when you're rushing. You'd put omega is v over r, and you forget to square it. But remember, omega squared is squared. All right, then. I finish this up, mgh. Okay, now I try to figure out what I can cancel. First of all, there's an m on every term, so all the m's cancel out. Next, there's an r squared here, cancels with the r squared on bottom there. And finally, the 1/2, the 2, cancels that 2 there. And now what am I left with? 1/2 v squared plus 1/3 v squared equals 9.8 times h. All right, 1/2 plus 1/3, what is that? Remember, you have to get common denominators. So common denominator is 6. So 1/2 becomes 3/6. And 1/3 becomes 2/6. 3/6 plus 2/6 is 5/6. So we have 5/6 times v squared. But v, we know the initial velocity was 20. So I can go ahead and plug it in now. 20 squared is equal to 9.8 times h. So h, get out my calculator, I get 34.01 meters. And there we go. So, of course, we've had a problem like this back when we did conservation of energy. You have a box at the bottom of a hill. You kick the box, give it an initial velocity of 20 meters per second. It slides up the hill. You want to know how high will it go. Very similar problem here. The difference, of course, is that because this is a sphere, the sphere can roll. And the rolling has some energy aspect to it. So everywhere I see kinetic energy, I have 2 different ones. And then I go through the same types of questions I ask in the initial state. Am I moving? Am I rolling? Am I some distance above the ground? Do I have a spring? Same questions as before. Of course, now with the rolling part. But of course, you know, if you're moving, then you're rolling. If you're not moving, then you're not rolling. So that's nice. And once you have all the terms laid out into zeros into zero spots where you don't have anything, that's nice. The next step, everywhere you see an I, you plug in the moment of inertia for your shape. Everywhere you see an omega, you replace it with V over R. And then you let everything cancel out that could cancel out, and then you have your final equation and you solve for your unknown. Okay? So it's a little bit more work than the original one from conservation of energy. You have some extra terms here. But really, that just makes for one or two extra lines of math. The method is the same method. It's not any more complicated to think about. It's just plug everything you can in, let things cancel out, and then you just crank out the algebra at the end to get your final answer. All right, well, let's try another example. Let's take, black example. Let's say, all right, I have a spring, and I've got a, let's say, a hoop. And what do? I push the hoop against the spring. The spring has a spring constant K of, let's say, 400. And I compress the spring by an amount of 1 meter. And then I let go. That pushes the hoop. The hoop rolls up this hill. And I know that this hill is 2 meters above the ground. The question is, how fast will this hoop be moving at the top? Now, just in case, we'll give some extra information. Let the radius of the hoop be, let's say, 0.2 meters. And let the mass of the hoop be 10 kilograms. Okay, in case we need the information. Maybe we don't, maybe things will cancel. But in case we need it, there it is for us to use. All right, let's get to work. Kinetic initial plus potential initial is kinetic final plus potential final. All right, initial state. I have compressed the spring, pushing the hoop against the spring, holding it there, waiting to release it. At that point, am I moving? Nope, I'm not moving, and thus I'm also not spinning yet. So 1/2 mv squared and 1/2 I omega squared, there's 0. Next, am I some distance above the ground yet? No, I'm still at the bottom of the hill, so no mgh. Am I compressing a spring? Yes, I am compressing a spring, so I have 1/2 kx squared. All right, initial state is done. Now I'll look at the final state. What's the final state? Well, I've let go of the spring pushes my hoop, the hoop rolls up this hill, is now at the top of the hill rolling along. At that point, am I moving? Yes, I assume I am. So 1/2 mv squared. If I'm moving, then I must be rolling, so 1/2 I omega squared. Okay, am I some distance above the ground? Yeah, I'm 2 meters up. So m times g times 2. And am I compressing a spring now? No, I've let go of the spring. The spring has pushed me away, so there's no spring anymore. All right, so hard work's done. Now I try to do my little fancy tricks. 1/2 kx squared stays the same. 1/2 mv squared plus 1/2. Now I have my I. Moment of inertia for a hoop or a ring is mr squared. And omega, I write v squared over r squared. And then, of course, m times g times 2 is still sitting there. And now we want to try to cancel whatever we could cancel. What can we cancel? Well, the r squared cancels this r squared. Can I cancel the m's? No. I can't cancel the m's because this term does not have an m. Remember, you're only ever allowed to cancel if every term has it. Now, of course, when I say that, I don't mean like this situation. This is two terms multiplied, one on top, one on bottom. That cancels. But what I mean when every term has to have it is cancel it from a whole term. Here's an m, here's an m, here's an m, but that doesn't have an m, thus I can't cancel all the m's. All right, so this is all I can do. Fine, then let's plug whatever numbers in I can plug in. 1/2, what was k? K was 400. What was x? I originally compressed it by 1 meter squared equals 1/2. The mass of my hoop was 10 times v squared. I'm looking for v. Remember how fast? I'm looking for v. Plus, let's see, 1/2 times m is 10 times v squared. And then plus 10 times 9.8 times 2. So that's what we look at here. Again, I want to solve this for v. So bring everything to one side, the v's on the other. 1/2 of 400 is 200, times 1 squared is just 200. And then 10 times 9.8 times 2, 98 times 2 is 196. I bring it to the left, so it's minus 196 equals, what's on this right side? 1/2 times 10 times v squared is 5v squared. Plus 1/2 of 10 times v squared is another 5, so this is 10 v squared. Okay. So 200 minus 196, 4, equals 10v squared. So v, square root of 4 over 10, which 4 over 10 square rooted gives me 0.63 meters per second. So I'm not moving very fast. It just barely gets up there. But it does. So that's nice. And there we go. Again, this is very similar to what we did before, only now that this thing can rotate, I have this extra 1/2 I omega squared term sitting there. But all I have to do, replace the I with whatever I should be, replace omega with v over r, and I solve it the same way I did before. And you're going to see, every single problem, it's always done this way. So if you could do these, you could do any of the problems. So I hope this was helpful. If you have any questions, of course, feel free to email me as always. I'll be happy to work through some problems with you. But definitely practice the problems that are posted on Canvas. Look at the solutions if you're having trouble. They should help you figure out what step you're missing or what, how to cancel things or whatever. But keep the little table of the moment of inertia with you while you're working these problems so you don't have to keep Googling them or things like that. And don't worry about, as I said before, don't worry about trying to memorize or anything like that. When it comes time for an exam, they will be provided on the exam so you don't have to look them up. But that's all I have for you here. So until next time.